Hi and Assalamualaikum. Okay, from the previous video, we learned the operation of the EMOSFET until we get the characteristic, which is the graph. Okay, graph ID versus the VDS versus the ID. Okay, now we take a look how we can get the transfer curve from the characteristic. Okay, the first diagram here, okay, this is the transfer curve that we get from the characteristic, okay, by plotting the VDS point, okay, plotting the VDS point here for each level of VGS, okay, into this graph. Okay, for the curve, the axis is ID, okay, and for the y-axis and for the x-axis is VGS. Okay, it's different. Okay, for the characteristic, the x-axis is VDS, y-axis is ID. Okay, it changed the VDS and VGS. So actually, for this one, the VGS, okay, VGS 6. When VGS is 6, so we plot here VGS 6, and this is the current. Okay, so it can transpose from here. And when VGS is 5, the current is here, some value here. Actually, for the ID, there is a value, but I just leave this one. Okay, you can look the detail in my notes. Okay, then for the 5 volt, you get here 5, and this is the ID. For the 4, VGS equal to 4, then we get the point here, VGS equal to 4 here. Okay, and when VGS is 3, okay, here the ID is equal to 0. Okay, so can you spot the difference between the JFET and the MOSFET characteristic and curve? Okay, for the EMOSFET, the curve is different for the different with the JFET and the MOSFET. Okay, where the curve is at the VGS positive. Okay, if compared to the JFET curve start from the negative VGS to positive VGS, and the DMOSFET is start from the negative VGS, and it can be at the positive VGS too. Okay, these two has similar curve. However, for the MOSFET here is different. Okay, now what information that you can get from the transfer curve? Okay, the same transfer curve. Okay, can you see the blue area? Okay, the blue area here. Okay, this is the area where the transistor is on. Okay, we can say the transistor is on when the VGS is greater than VT. Okay, for this example, the VT is 3 volt. So as long as the VGS greater than 3, so it can the transistor can be on. However, if the transistor is less than VGS, less than the VT, okay, so here, okay, the transistor is off. Okay, you can see the ID equal to 0. And now we go to the mathematical equation for the EMOSFET. Okay, we know that this curve, okay, from this curve, it can be transformed into the mathematical equation. Okay, the transfer curve that obtained from the EMOSFET characteristic is not like a parabolic curve. Okay, remember the parabolic curve? Okay, the curve that we seen for the JFET and the MOSFET. Okay, therefore the Shockley equation cannot be used because this one is not in a parabolic curve, so we cannot use the Shockley equation. And then therefore this graph okay, or this curve can be defined, is defined by the equation here. Okay, ID equal to K multiplied with VGS minus VT squared, and the condition is here for VGS greater than VT only. Okay, so what is K? K is another variable, okay, that has a formula here. Okay, so K equal to ID on divided by VGS on minus VT squared. Okay, so if there is no K value is given, you have to find by using this formula. Calculate this first, and using the ID on, VGS on, and VT here. Once you get the value, and you insert its value in this equation. Okay, so the unit for the K is actually milliampere per over volt squared. Okay, so here is ID on. Okay, so what is actually ID on and VGS on? The ID on and VGS on actually values where the device has reached its saturation level. For example, at this graph, okay, for the VGS equal to 6, okay, and then the ID now, ID is 10 milliampere. So we get this value. We say that this is the VGS on and ID on, okay, for this level. So for the second level, the VGS is 5, and let's say this is 8 milliampere. So this is the ID on, okay, for this level, and VGS on for this level. So it means that for each level there is their own ID on and VGS on value. Okay, but normally we take the highest saturation level, okay, which is this one. Okay, the highest saturation level shown in the graph, okay, to insert in the equation. Okay, now you see, we see that this point is actually with this S saturation, or we say that this is the VP. However, in the EMOSFET, we normally we don't need the VP value. Okay, only JFET and DMOSFET will use the VP value. For the EMOSFET, we only use the threshold value. So this is the major difference between EMOSFET and JFET and also DMOSFET. Okay, now we take a look at the important relationship for the EMOSFET. The first one, the IG equal to 0. Okay, this is similar with other transistor. So this is because of silicon oxide layer that prevent the electron flow through from the N channel to the gate terminal. That's why we get IG equal to 0. And then the ID equal to IS. Then the equation now, okay, we are not using Shockley equation, but we use this equation. So ID equal to K equal to VGS minus VT squared. Okay, so the value of K, okay, this is the formula, ID on divided by VGS on minus VT squared. Okay, so here the VT for the N channel, VT for the N channel EMOSFET, sorry, not DMOSFET, for the EMOSFET is positive, and for the P channel is negative. Okay, now we want to plot the transfer curve. Okay, I give one example to explain how to plot the transfer curve. Okay, plot the transfer curve for the device that have the characteristic of ID equal to 0.5 milli multiplied with VGS minus 4 squared. Okay, actually this equation is obtained from the formula that given for the ID, which is ID equal to K multiplied with VGS minus VT. This is VT. Okay, so in this example, VT is 4 and K is 0.5. Okay, from this equation, now we know that the transistor is off if VGS less than VT. So we start to plot the graph when VGS is above the threshold value. Okay, so the ID is 0 for the VGS less than 4. So we draw here. Okay, for the less than 4 is ID equal to 0. Next, for the after the VT equal to 4, we set VGS is 5. So here, the point is here. Okay, insert this value. So calculate 5, insert 5 in this equation. Okay, then calculate, you get this answer. It means ID is 0.5 milliampere. Okay, and then the next point is 6 volt. Okay, insert in here in this equation, then we get the answer is 2 milliampere for the ID. And the process will continue for the next point, 7, and you get the answer for each for the 7, and this is 8 volt you get for the 8 milliampere. Then you can plot here. You can choose whether 4 or 5 point to plot this graph. Okay, now we go to the last part in this chapter, which is the data specification sheet for the EMOSFET. So in this specification sheet, the EMOSFET parameters are divided into 4 tables, but sometimes in some data sheet it has more than 4 table bytes. But for in this chapter, we just want to focus in this 4 section. Okay, the first one is maximum rating. Second is off characteristic. Third is an on characteristic, and fourth is small signal characteristic. So this is one of the example for the EMOSFET. Okay, now for this specification sheet, it contains 3 models. Okay, it has 3 model here, and then okay, this is the symbol, and we can see the top view. Sorry, not top view. This is the physical. Okay, physical of the EMOSFET, where it has numbers for the each leg or terminal, source, gate, and drain. Here you can refer this. Then we go to the data specification sheet for the absolute maximum rating. So this is the VDSS. VDSS actually the VDS. Okay, drain to source voltage. Maximum value for this one is 60, and then the ID, the maximum current drain, here this value. Okay, for each model. Okay, be careful when you looking for the information in this specification sheet, because it has 3 model. Okay, you should refer to which model that you are using. Okay, and then the PD is the maximum power dissipation. Okay, for the transistor. And then this is the off characteristic, okay, where there is the IDSS, okay, for each model. And this is the on characteristic, where we must find the VGS-TH here. VGS-TH is actually the VT, the threshold voltage, okay. You get threshold voltage, and this is the value. Okay, and value for each model. Then we have ID on here, okay, ID on, observe, okay, and here is VDS on. So this GFS is actually forward transconductance that is useful in AC analysis. Okay, that's all for the EMOSFET, and I hope you can revise, you can watch it again and again, and we finished our chapter 1, and we will continue, we will start with another lecture for the second chapter. I hope you can study very well, and if do you have any question, you can just drop your question via WhatsApp group or via Google Classroom. Okay, thank you for watching.